Hi class, this is Dr. Martino. This is the third full lecture in the Respiratory Physiology lecture series. The last time we met, we finished up talking about estimating compliance using this curve, lung volume change over pleural pressure. We went through some simple equations and how we could estimate transpulmonary pressure from this for both for inspiration and expiration, and got the basics down to compliance, right? Because compliance is the change in volume over the change in pressure. It's how stretchy, how easily you can open up a stretchable compartment. In this case, happens to be the lung, works the same way with rubber bands. And how compliance is different than recoil, which recoil is associated with elasticity, which is the trait of being able to be deformed. Tissue can be deformed and come back essentially to its original form. One thing to be said about this and to be reminded is that this is the compliance curve, an estimation of the true compliance curve for a breath cycle, inspiration and expiration, and that the line in the middle here, the average line, is actually incorrect in that it should be curved, and we're going to see that in the next slide. But for the purposes of this complicated explanation, it's just easier to be able to look at this entire concept using a straight line for the slope. So that's why we use it. It's good enough for what we're trying to do. This new curve, the next in line, represents, or this new graph represents compliance, but three different compliances. The green one in the middle is normal. The green one in the middle is normal. This blue is high compliance, and this orange represents low compliance. Notice how this graph here uses transpulmonary pressure directly. Remember, and transpulmonary pressure is a type of transmural pressure, which equals the alveolar pressure minus the intrapleural pressure. I'll read some of this for you and then we'll get going with this. So the compliance curve is sigmoidal. So this is what it actually should look like. And so this would be something like that. Actually, something like that, if we were to draw it accurately. Due to elastic properties of the lung, compliance is due to the elastic properties of the lung. It is affected by the lung volume. So the more air you have in the lung, that changes the properties of compliance. Low lung volumes, during that point at low lung volumes, compliance is relatively low, generally speaking. The lung is compressed by the chest wall. At high lung volumes, compliance is also relatively low. The lung is stretched to its limit. You ideally want to be in this green area, Okay, let's talk about compliance in terms of how it relates to disease. Disease is usually an extreme physiological state, right? It's not normal. And so much like exercise being an extreme physiological state or altitude or being underwater, disease helps us better understand normal physiology. So you want to be the green. The green is normal. Let's talk about the blue for a second. Compliance is abnormally high in the blue. Lungs are prone to collapse like a paper bag and loss of elastic properties. So the blue, you can imagine a situation where somebody has the disease emphysema. Emphysema is in a category of respiratory illnesses that are classified as COPD, or chronic obstructive pulmonary disease. Chronic obstruction. The first thing we got to get off the table is that emphysema, chronic bronchitis, and asthma are similar in that they're all obstructive diseases. However, emphysema and chronic bronchitis are chronic obstructive pulmonary diseases. So they're not the same. They have similarities. Asthma has a different etiology, right? It is a different mechanism that created it, and it's very different in the way it progresses. Emphysema and chronic bronchitis are different also. They're more similar to each other than they are to asthma, but they're both under chronic obstructive. So chronic obstructive pulmonary diseases, although there is the similarity that the obstruction part is similar to asthma, the way they got created and then the way they progress are different. So asthma is a different animal. This is not asthma. So what ends up happening in emphysema is that due to lots of different reasons, smoking primarily, smoking, being around lots of harsh breathing environments, causes the lung tissue to start to break down. So if we can imagine this alveolus representing one of 8 million or so alveoli, these alveoli are connected to the rest of the lung via these things called elastic tethers. And this allows the airway here, the alveolar ducts, the terminal bronchioles, and the alveoli to stay more open than they normally would. Remember, the lung is trying to get to 0% of total lung capacity. It's trying to completely collapse. And the chest wall is trying to get to 60% of total lung capacity. And they come to this compromise of 40%. There's lots of structural pieces, parts of the mechanics here, that prevent the insides of the lung and the lung to collapse. So these tethers, these physical connections from the rest of the lung to the actual airways, help keep this open. That's important. What ends up happening in emphysema is that, and this is not exactly what I'm trying to do, so I'm just going to erase each individual one here and redraw them. That you get breaks in the tethers. And when you get those breaks in the tethers, and you don't get them all at once, the lungs of emphysemic patients are more prone to collapse. Now, it's sort of counterintuitive, and I'll tell you why it's counterintuitive. If you look at the curve for the emphysemic patient, you'll notice that the slope of the curve is greater, right? There's a greater slope. So it's mathematically true, right? If you draw a straight line, or approximate straight line, and you compare it to this straight line, give or take, this slope on the left is greater than the slope on the right. What that means is that you have a greater per unit change in lung volume for every change you have in transpulmonary pressure. So the bottom line is that emphysemic patients have a much easier time than you and I at taking in a breath, which sounds great, except except the way they got there was through disease. So what ends up happening as these tethers start to break, and essentially, right, this is the outer wall of the lung, and then you have the pleural space, right, and then this is the chest wall. The connection between the chest wall through the pleural space to the alveoli has essentially been severed, right? It's broken. The more you break that connection, the more the chest is going to start to win this tug of war that's going on so that it could eventually get to 60% total lung capacity, excuse me. What does that mean? Well, if you could measure the perimeter of a chest wall, the thoracic cavity, in a non-emphysemic patient, and then you knew they were going to get emphysema and then measure it later on in the disease, you would find out that the chest wall has actually gotten bigger. So people's chest becomes barrel-chested. But it got there because they're starting to have these breaks in the connection, and so the chest wall, which is helping essentially to keep these airways open through the pleural space, the water gap here, and these tethers, is no longer able to do that. But it also doesn't, so that's the negative effect here, is it's not helping to keep these things open. And the positive effect, I guess, for the chest wall, if you're looking at winning the tug of war, is that the chest wall is winning. So when an emphysemic patient goes to take in a breath, it's very easy. Very, very easy compared to you and me. The problem with them is when they go to expire, you and I who have normal lungs, use a passive mechanism. We turn off our diaphragm, and then the elastic properties of the lung allow it to compress back to its original form, and you expire. So we use an active system. We use ATP to open up the lungs via the diaphragm muscle. And under normal circumstances, the diaphragm is doing most of the work. And then on the way out, we just relax and we expire. So we're using minimal energy on expiration, right? However, if you compare that to an emphysemic, they don't have as much energy that they need to use because they don't need to overcome as much resistance or friction. That's great. So they're saving some energy there. But on the way out, because of the loss of elasticity of this tissue, because of this connection being broken, you now all of a sudden have to bring in the intercostal muscles. You have to bring in transverse abdominis. You got to bring in rectus abdominis. And you got to actively be expiring. So they're using a lot of energy to expire, where you and I are not using any energy. So even though they make up for the energy on the in, that small decrease doesn't even come close to negating the amount of energy that they have to use to expire. So easy in, very long and hard out. And that's one problem, right? So that they're using lots of energy to expire. Imagine doing this 24 hours a day. You would get very, very tired. They can't exercise because they're just breathing. They're just sitting, standing, walking. Then when they expire, these green broken tethers that were keeping, right, that were keeping this connection here to prevent the airway from collapsing, no longer can do that. So on expiration, and they're using, remember, this is forceful expiration, what ends up happening is that these airways, which were being held open by the tethers, start to constrict. So as you're trying to blow air out to get rid of air, to get rid of CO2, you can't, because many of those airways, the alveolar ducts and the terminal bronchioles, or the bronchioles, are collapsing. And so you're trapping CO2. On the way in, it's easier. They don't get collapse. So they're bringing in some oxygen, but they're not bringing in as much oxygen because the percent change isn't as great. So you have this multiple problems that you're running into because you have this massive increase in compliance, but for a bad reason. So that's emphysema, that's COPD, very similar to chronic bronchitis. Again, chronic bronchitis and emphysema are obstructive diseases, just like asthma, but asthma's different. Asthma doesn't have this problem with the breaking of these tethers and the collapsing. It's got a different set of issues, and the way it progresses is very different. Okay. So that's what happens when you get a pathological increase in compliance. You can also get a pathological decrease in compliance. Compliance is abnormally low. The work of breathing is increased, fibrotic lung. So when your compliance is extremely low, imagine, like a coal miner's lung, black lung. The tissues, let me erase some of this stuff. The tissues start to get gunked down. So you've got these tethers, right, that are attached. So that's fine and dandy. But they start to get, imagine that they start to get glued down. Start to get more attached to one another. Less compliant. So now it becomes much more difficult to even intake a breath, right? To even intake a breath. And there really isn't much of an increase in elasticity here. It's just stiffer. It might be slightly easier to exhale. That's questionable, but for sure it's harder to take in a breath, and it's probably a little bit harder to even exhale. So these people have a different set of problems, and here the compliance is abnormally low, right? Abnormally low. So these people are also they could be put on ventilators. Both of these groups are on ventilators. They probably need supplementary oxygen, right? Because they can't get enough oxygen in, and they can't get rid of enough CO2, so they're having a buildup of CO2. Remember, buildup of CO2 decreases the pH, increases acidity. That needs to be dealt with by the kidneys because the lung can't fix the problem. So over time, both of these diseases progress in a different way, but they're both bad, right? And we don't have we have treatments for both of these, but there's not much we can do for them. They progressively get worse. Now let's talk about a different part of compliance. An additional factor that affects compliance is the stretchability, right? There are two major factors, the stretchability and something called surface tension. Surface tension. And surface tension is a force that is caused by water molecules being attracted to one another at what's called an air to water interface. Now there's two places that you can see this. In this picture below on the right here, you have a water walking bug. There is tension, so the water molecules on the pond attract one another, right? So there's a bit of a bond, a weak bonding that occurs there. They're attracted to one another. And when you have air interfacing with that, it sort of increases this attractability. You can think about it that way. It's not necessarily true. If an animal, in this case the bug, can distribute the load in a certain way, because of this air to water interface, this surface tension, they can essentially walk on water, which is what this bug does. Okay, so that's on a flat air to H2O surface. This is also relevant in the respiratory system because the alveoli are spherical and they also encounter surface tension. So what does it say here? Attractive force between H2O molecules at the air-water interface. The barrier on planar surfaces, which allows this to happen. Collapsing force in spherical structures. So in flat water to air interfaces, it becomes a barrier, and that allows bugs to walk on water. But in spherical structures like the alveoli, this surface tension actually increases the ability for alveoli to collapse, which is not a good thing. Now let's look at, we're going to continue on with this compliance, idea of compliance and surface tension. In this figure, you have the change in lung volume in liters on the y-axis, and you have on the x-axis pleural pressure. You have the first compliance curve for a breath cycle that we looked at. This is with air inside the lung and water outside the lung. In the newer compliance curve, there's water on the inside of the lung and there's water on the outside of the lung. As you can see, the slope of the compliance curve for the saline or the water-filled lung is greater. You can also see that this hysteresis is what causes elastic structures to sort of bow out on the way out when you're pulling them on the way out and bow out on the way down. So the lung is an elastic structure. You don't have this hysteresis, right? So this hysteresis, this bowing out, is partially caused by the elastic properties of the lung and partially caused by surface tension. Here, you only have a water-to-water interface, so the surface tension is extremely low. And the reason that the two surfaces, the inspiratory surface here and the expiratory surface here, don't come and touch is because there's actually physically water between them. Here, there's only air. So what does that mean? A saline-filled lung has no air-to-water interface. It has essentially no surface tension. Very little collapsing pressure to overcome. So in the lung to the right, you have a high surface tension, which causes this collapsing pressure. Small changes in transpulmonary pressure in this lung will cause a very high compliance, right? You can actually measure this. If you drew a line straight down, which I'm not doing very well, from beginning to end, and you measure this distance, and then you draw a line straight down. I'm not doing this very well, and you measure the distance. That basically gives you an idea of how much transpulmonary pressure you're going to need, and clearly this one on the left is less than this one on the right. Now, I know you're saying to yourself, but Martino, that says pleural pressure. Yes, but there's a way to estimate transpulmonary pressure because the transpulmonary pressure is essentially the slope of this line, and at zero, at the end of an inspiration, at the beginning of an inspiration, end of an expiration, right? Transpulmonary pressure and pleural pressure are equal and opposite in sign. And so you can then say, you can make make a statement about transpulmonary pressure. Don't get caught up in that. Just use the big ideas for now. In the normal lung, moderate surface tension, the air to water barrier, right? You have surface tension, it's relatively compliant. You have a good compliance, and the surface tension reduced by surface surfactant. So how do we make a normal lung? So this is the ideal, right? You're not going to get this in a normal lung because of the air to water interface. But how can we make a normal lung more compliant? How can we reduce the collapsing pressure? Well, we in mammals, in most animals, have a substance called surfactant. Surfactant is a detergent. I like to think of detergents or soaps. And I like to think of things in simple terms, right? So a surfactant, a soap, is essentially a molecule, whether it's engineered or not, they occur in nature, that has two sides to it. And one side is hydrophobic. This is how soap works. So it can interact with fatty hydrophobic molecules. Right? Doesn't like water. The other side is hydrophilic. It can interact with water molecules and it's soluble. So this is called amphipathic, to have both of these characteristics. Amphipathic. How does that help us? Well, membranes, animal cell membranes, have fatty substances in them, phospholipids, right? They have cholesterol in them. Those are hydrophobic molecules, oftentimes in dirt. So if you think about washing your hands, if you're dealing with oil, is a hydrophobic molecule. You're changing oil on a car or a tractor. Hydrophobic. If you just use water, it is very difficult to solubilize the oil because oil and water don't mix very well. But if you add a substance like a detergent, like a surfactant to that has a hydrophobic side, the hydrophobic side can embed itself in the oil or the hydrophobic molecule you're trying to rid. And then the hydrophilic side will interact with the water, and that's how soap and detergent works. And so, right, and if something is really oily and really hydrophobic, then you got to use more soap, and it works. So that's the basic gist. Okay, so what ends up happening here? You want as much compliance as you can get without having a disease like emphysema or chronic bronchitis. You're not going to have a water-filled lung because if you have a water-filled lung, you can't breathe. You're not a fish, right? You don't have gills. If the alveoli become filled, you either have aspirated, you've somehow accidentally gotten water down into your alveoli, or if you get pneumonia, you have another problem. Okay, water in the lung is a bad thing. Water outside the lung is normal. So we're not going to get this. This is not going to happen. This is pathology in and of itself for humans. So how do we get this normal lung to be more compliant? That way it's easier for you to breathe in. Well, let's draw a representative alveolus. This is an alveolus. There's air in here. Okay, there's water out here. So there's an air to water interface. There's surface tension on an alveolus. The water molecules want to be close to each other. And because they want to be close to each other, they essentially compress the bronchial and they compress the alveoli. And essentially that will cause or could potentially cause the alveolus and the bronchial to collapse. Well, that's bad. Okay. And you have to overcome that collapsing pressure, that force, in order to be able to take in a breath. Without surfactant, it would be really hard to breathe. When has this happened in your life? The first breath you ever took was the hardest breath you'll probably ever take. And the reason that is because when you're first born, you don't have you're making surfactant, but you haven't actually taken actual breaths where you have an air to water interface, or you have a plug that's in your throat. And babies, when they're in their mother's womb, are practicing breathing, right? But there's not actually breathing going on. So there is some surfactant, but there isn't a lot of surfactant. And so that's the hardest breath to take because you have very little surfactant being produced. Your body is capable of doing it, it's just not doing it yet. So you need a stimulus to start producing lots of surfactant. I don't know if this practice is still in vogue for doctors that deliver babies, but it used to be. And one of the practices that they used to do, I think, they might still do it, was for the nurse or the doctor when a child was born to pat that child on the butt, right? To pat where all the padding is. And the reason they did that wasn't because they were trying to hurt the child, was because they were trying to very gently agitate the child. And by agitating the child, that child would take in more air, right? They would expand their lungs, expand their alveoli because they're going to scream. They're unhappy. You just did something to them that they do not like. And by doing that, the more you expand the lung, the more surfactant you produce. So as that happens, they start producing a lot more surfactant because they're taking deeper breaths, and then every subsequent breath gets easier to a point. And so now you have a baby that can breathe very easily because of the surfactant. So I'm not sure if they still do that, but that's the reason. That was the rationale behind it. If you were born early, prematurely, and I think it's somewhere between 20 and 26 weeks, it might be before 26 weeks of gestation, your body's still not producing surfactant. And surfactant is produced by type 2 alveolar cells from the lungs. If you're born early, you don't have the ability to produce this detergent that decreases surface tension, that decreases the collapsing pressure essentially on the lung alveoli. So therefore, you need to be placed on a positive airway pressure ventilator. The ventilator positively pushes air into the alveoli and pushes oxygen. The problem with that is that you're doing this under high load, high force, to very young, injury susceptible tissue of the airways of children. And if you do this for long periods of time, and we know this, we essentially did these studies, and so we have children that exist that would be of my age, in the millennial age, before there was artificial surfactant, where they were preemies, and they were on a ventilator for weeks. And we know that those individuals, when they became adults, have more respiratory related issues than children who weren't on ventilators. So it's not good. Somewhere in the last about 20 years ago or so, 25 years ago, I can't remember the actual date is, we invented artificial surfactant. And that artificial surfactant was able to be injected into the babies, and this would help them increase their compliance, decrease their collapsing pressure, so that when they were on the ventilator, you could use less pressure to help the baby breathe and therefore cause less damage and even maybe pull them off of the ventilator sooner, which ultimately long term is better for the baby. So we know what happens when surfactant isn't available. It's not good. So how does surfactant work? Well, let's draw an alveolus again. Remember, the water molecules want to get close to one another. They just like to, and this causes this collapsing pressure, this surface tension. What the surfactant does, because it's an amphipathic substance, is it jams itself in between the water molecules. Therefore, the attractiveness from one water molecule to the next decreases, and that means that the collapsing pressure on the alveolus decreases. So then it's easier to take in a breath. And the bigger the breath you take, the more that type 2 alveolar cells make surfactant. So you have more surfactant available, and it's easier to take a breath. So if you do this exercise where you take a deep breath, a big 360 degrees around your torso breath, big belly breath, you'll notice that the next couple of breaths are much easier to take, right? Inspiration is easier, and that's because there's more surfactant being produced. You'll also notice that if you have really bad posture and you're hunched over and the anterior chain of your body, the rectus abdominis, the pecs, the shoulders, the hip flexors are all tight, that it's harder to breathe. And so this then causes breathing problems. I don't want to digress into that, but it's a sort of an interesting thing to think about sitting. I know in my 3300 class, we have these Martino moments where we talk about why sitting is so bad and the types of things we can do to make things better. And in addition to the structural, muscular, tendon, ligamentous issues that we can begin to fix, we can also fix breathing. And part of it is postural. So we're not going to get into that. We're not going to digress. But so this is how surfactant works. It jams itself between the water molecules. You have less attractiveness between the individual water molecules from one another, which causes less of a collapsing pressure. And so it's easier to breathe. Some important facts about pulmonary surfactant. Pulmonary surfactant is a mixture of phospholipids and protein, right? So you have a hydrophobic molecule, you have a hydrophilic molecule. Surfactant works on both. It is secreted by type 2 alveolar cells. It lowers the surface tension of water layer at the alveolar surface, which increases lung compliance, thereby making it easier for the lungs to expand. It decreases the collapsing pressure. Its surface tension is lower in small alveoli, thus stabilizing the small alveoli. And we'll talk about that in the next slide, and I'll show you an example of how this works better, surfactant, in small alveoli than large. A deep breath increases its secretion by stretching the type 2 cells. Its concentration decreases when breaths are small. So when you're not breathing fully, which most people are not, they have bad breathing patterns for lots of different reasons. That causes lots of problems, hormonal problems, and that can be fixed. So a lot of people have muscular problems and hormonal problems that are generated, at least in part, by this not breathing correctly and not having good posture. Production in fetal lung occurs in late gestation. So if you're born before that happens, then of course you're going to have problems breathing. Here you have an example of how surfactant can protect small alveoli from collapsing. So the first thing you need to do is you need to memorize, this is called the law of Laplace. the law of Laplace. And the P stands for the collapsing pressure, right? The collapsing pressure, this pressure that's pushing in on these alveoli. And the collapsing pressure is equal to 2 times the surface tension. Remember, that's the tension at the air to water interface, divided by the radius of the structure. So that needs to be memorized, number one. If you have an example, and this is not unrealistic, where you have a bronchiole that connects a large alveolus and a small alveolus, okay, you're going to have some issues with the small alveoli getting as much oxygen and getting rid of as much CO2 as it can, and with the small alveoli potentially collapsing much more easily than the large alveolus. So that's not good. So how does this come into play? Well, let's read the bottom here and then we'll look at this. With no surfactant, surface tension is the same in large and small alveoli. So, and the reason that is because there are more water molecules around the big alveolus than there are around the small alveolus. So the actual amount of tension on the surfaces of both essentially are the same. And it's due to a concentration issue, right? There's more concentrated water here than there is here. A small radius equals greater collapsing pressure. So why is that? If the surface tensions are the same, then why is that? And we're going to show you that in a second. With surfactant, surface tension is reduced, especially in small alveoli. Surfactant is much more concentrated. So let's take an example. The collapsing pressure for the large alveolus. I'm going to make up some numbers that aren't necessarily real. Doesn't matter. 2 times the surface tension. Okay. Let's say the surface tension is 2. And let's say that the radius of the large alveoli is 4. Just don't worry about units. It's just 4. So if you take this out and you do the simple equation, it's 4 divided by 4 equals 1. Now we do the same thing with the small alveolus. We know that these two numbers are the same because surface tension is the same. But let's say that the radius here is 1. Do the simple math. And you see that the collapsing pressure in the small alveolus is 4 times greater than that of the large. So there's a 4 times greater chance that a small alveolus, in this particular case, is going to collapse versus a large alveolus. It's kind of a big deal. Now what happens? So this is with no surfactant. On the right side, if you redo the same thing, and now you have surfactant involved. Let's imagine that the tension, and this is what happens, the surface tension decreases. Well, the surface tension decrease in the large alveolus is going to be less than that in the small alveolus because there's less surfactant that's going to be here, concentrated around this. It's spread out more. So let us say, right, let us say that instead of having a surface tension of 2, right, remember this is still 4. This is still 4. Let's say that it's 1.8, okay, 1.8. So there's still a decrease. It's just not a very big decrease. So you multiply 2 times 1.8 and you get